So this is the second videos for the physics crash course for section 3 of GAMSAT. If you haven't already seen the first one, they're kind of sequenced. So if you're coming from a non-science background, which what this is mostly designed for, you'll probably want to watch that one first and then work your way through. So I'll probably refer to some of the things that I've mentioned as they go. I've created a playlist as well. So in this one, what we're going to do is we're going to be going through a few different things. It's a bit of a mishmash, but it's trying to finish off the rest of the kind of kinematics topic. So projectile motion, and then we'll also be looking at circular motion in both the horizontal and the vertical plane. And then as well as that, connecting gravity a little bit from the previous video as well. And then we'll be going through torque, work, and then some concepts of potential energy and the conservation of potential energy as well, or the conservation of energy, I should say. So we want to be looking at this from more of a principles perspective. So I'm going to be teaching it in terms of kind of the key drawings that you can take from each of the topics and how that can help you kind of reason with questions. Anything to do with formulas, I'll probably make mention and use some formulas throughout, but most formulas, particularly in physics, are already provided to you and all the variables defined and everything. There's really no need to memorize any of the formulas that I mentioned today. What we want to do is get a familiarity with them so that we can very quickly use them and understand things like proportionality, and understanding the relationships between the variables to look at more qualitative analysis as opposed to too much quantitative stuff. The maths, though, is kind of unavoidable. So the first thing is we're just going to look with projectile motion. So I'll put that here. We're looking at anything being, projected into the air and then back down onto the ground or to some platform. So if we think, for example, something really simple, let's just take like a soccer ball or something, and if it's on the ground and then it gets kicked, it'll follow a parabolic path and then land on the ground again. And we're going to ignore any effects of bouncing and all the rest of it. It's just from when it leaves the ground to when it first touches the ground. And so what I might do there is draw in the path a little bit more symmetrically, as best as I can. There we go. And so the key thing is we want to understand the ball's movement and both its horizontal and vertical components. So we talked in the first one about the vector components, and that's exactly what we're going to do here, and understand how they relate to the ball's movement. So first of all, as it's kicked, let's say it's kicked on an angle of 30 degrees. If it's shot out at 30 degrees, it'll immediately start arcing, right? Because the reason for that is as soon as it's in the air, let's draw it here. As soon as it's in the air, let's draw it here, then it'll still have gravity kind of pulling down on it, right? And so that's what's going to kind of push it in this bending path overall. But more importantly is when it was launched, I'll get rid of that again, it had a horizontal component and a vertical component, like this. So as we go through, if we now draw the ball at this position, the key thing is that its horizontal component will be constant, because there is no, assuming no air resistance or anything, there is no horizontal forces acting on the ball once it's then left the foot of the person or once it's been projected into the air. The only thing that's impacting it is gravity, and gravity pulls downwards. So it's competing with that upward force, right? And that upward movement. And so what we'll see as a vector is that vertical vector will be decreasing as it goes along its path. So you can see it's a shorter arrow now. And what does that mean? It means that the net direction of that vector will be at a shallower angle, which explains the curve of the path, right? And this is parabolic, not circular. So it has more of like a U shape to it. So it's not a continuous curvature. When it reaches the top, this is one of the most important points. At this point, again, its horizontal motion or its horizontal vector is still constant, the same as it was when it was launched. But by this point, gravity has now completely cancelled out that vertical motion. So it's now got zero vertical motion, which means that it's actually moving perfectly horizontally in that instant. And then as it starts to fall, we'll see gravity start to add to the vertical, and it'll actually start to now point downwards. But again, that horizontal will be the same. And then finally, when it reaches the ground, it'll again have that there, and gravity will have had some impact as well, but it doesn't really matter because it's hit the ground at that point. So we can kind of visualize what's happening to the vectors as it goes, right? So think of it as animating as the ball moves across that arc, the horizontal is remaining constant and the vertical is getting smaller, and then it reaches 0 when it hits its maximum point, and then it starts to point downwards and increase in that downward trajectory as it continues moving in the falling phase. And so what that means is that we can solve, when we're talking about the maximum height which occurs at the peak here, this here would be the maximum height. This is a key thing in solving anything to do with projectiles. We can make the assumption that at this point, its vertical velocity is completely equal to 0, right? So it has no vertical movement. It still has a horizontal movement, but its vertical movement is completely separate. And that then allows us to split the projectile path in halves and then solve like that, right? And so the other key thing is that when you're doing any calculations, you want to make sure that you've separated your horizontal and your vertical components. And the key thing is, given that horizontal is remaining constant throughout and there's no horizontal forces acting on it, what that then means is that the vertical components is going to determine everything about the path, right? The only thing the horizontal component will determine is how far the ball actually goes, or how far the projectile goes. That's still somewhat dictated by the angle and the vertical components. But if the ball is in the air for a certain amount of time, well then if it's moving faster in the horizontal direction, then it's going to move a greater distance in that same time frame as a ball that has less of a horizontal velocity. That's the only thing that it can impact. But ultimately we're more concerned with the vertical components. And so in terms of working out the maximum height, they do give you formulas. So we can do, for example, v equals u plus at, where this is the final velocity of an object. U is the initial velocity, and then a is any kind of acceleration, and then t is time in seconds. So we can take the rising phase, or the ascending phase, we can split it in half, and we can say, okay, well, from here to here, it initially started, its initial velocity, and we're going to do all vertical here. Let's say that its initial velocity was 30 meters per second vertically, right? It's very, very high. Plus, and then acceleration, that is a negative direction. It's negative 9.8. Let's go negative 10, given its GAMSAT. So negative 10, always acting on it, because remember, gravity is an acceleration. And then time in seconds. We're going to solve for time. And the way that we solve for time at this point is we let the final vertical velocity be equal to 0. And that tells the equation, okay, you're at the maximum then. So 0 is equal to 30 minus 10t, and then we can just solve that mathematically. So we can minus the 30 and then divide the negative 10, and we can get 3 seconds. So it should take the ball 3 seconds under those numbers to reach its maximum height. And then because projectiles are symmetrical about their turning point or about their maximum position, then it means that the total flight time, t total, should just be twice that amount. It should take 3 seconds to rise and 3 seconds to fall. So therefore it's a 6-second flight overall. So yes, there's some calculation in it, but a lot of it is based on assumptions and principal understandings of how projectiles work and how that motion works, and understanding that it's broken into vertical and horizontal components like that. Cool. If you wanted to then know how far it traveled, I don't think they would go that far into it because that's a bit more technical. But again, if its horizontal velocity was, say, 40 meters per second, these wouldn't make any sense for 30 degrees, so ignore that. If you did like Pythagoras and a bit of trigonometry on it. But the total distance here is much, much simpler. You go, okay, well, that's horizontal. So I don't want to consider vertical velocities. I want to consider the horizontal, which is 40. And so therefore, that would just be distance is equal to speed times time. So you can see that would be 40 meters per second. It's in the air for 6 seconds. It must travel 240 meters. So it's definitely not a soccer ball because that's a hell of a kick. So it might have been something fired out of a gun or something like that. But that's projectiles. So the key things that we want to take from it are that at maximum height, vertical velocity, so I'll do VV, vertical velocity, is equal to 0. The other thing is that its path is symmetrical. So therefore, we'll say t to get to the maximum height is equal to half of the total. So therefore I might do that a little bit differently. If we've got T max, then 2 times the time to get to the maximum position is going to be the total flight time. We can assume that the 2 halves are equal. And it also means as well that things like, for example, the launch angle of 30 degrees, that would mean that the landing angle should hit the ground at a 30-degree angle, assuming the ground is flat. Everything else, it's a direct mirror image. We can make those assumptions. And that often can either help you answer questions more quickly, or it can help you do qualitative analysis without having to actually get no calculator, without having to do any calculations, anything like that. Cool. So we've done that. So vector components, max height, symmetry. Now we've got to look at raised platforms as well. I don't think that this is very likely, but I'll throw it in anyway, just in case. So in that scenario, that was just from ground to ground. But if, for example, there was a tall building and the ground below, and then something was being thrown in the air at an angle, right? But then was still falling to the ground, you can clearly see it's not symmetrical about its maximum height. Like this now, it's asymmetrical. So we do have to split that into 2 parts. So I like to just kind of visualize it and go, okay, well, I can split it into 2 halves, this half and that half, right? So the rising phase and the falling phase. And I can just kind of add them together at the end. So in the rising phase, this here acts as like my max height almost. And so I, again, just go through V equals U plus AT. So I can solve it here, T equals V minus U on A, and where V is 0, right? So 0 minus the initial velocity over A. And again, all vertical numbers in that case. We can work out the time that it takes to get to that point. And then from there, you can work out the maximum height as well. So again, they would give you these formulas. So V squared equals U squared plus 2AS, where S is distance or displacement. So we can solve that for displacement. And so again, we can go 0 squared minus initial launch speed divided by 2 times -10, because again, acceleration is gravity, which is in a negative direction. And don't worry about the negative, because your minus here, you'll have 0 minus initial velocity squared. That'll give you a negative as well. They'll cancel out, and then you'll have a positive distance. So that would be S here, and they would most likely give you the height of the building. So if maybe the height of the building is 80 meters, then what that means is that on the falling phase, you now know the total displacement is actually 80 plus whatever you get here, right? So let's just say this comes out as 40, then it would be 80 plus 40, so you have 120 meters to fall. And the idea is that even though it has a horizontal component, and I won't fuss about that again on this one, really you can just think of any projectile as something being thrown in the air and then falling back down again, right? Because the vertical components of me, say, throwing a tennis ball directly up in the air and straight back down into my hand is exactly the same as if I was to throw the tennis ball at an angle, but with the same vertical component, right? It'll still have the exact same behavior. It'll act in the same way. It'll hit the ground at the same time. So I don't really think much about the horizontal component. I'm just kind of going, well, I need to throw a ball from this position to this position. How long is it going to take? Or how long is it going to take for a ball to go from 120 meters to the ground under gravity, right? And so there I can do V equals U plus AT. And so time equals V minus U on A. Actually, no, that one won't help me. That one, I would use UT plus half AT squared is equal to S. And again, formulas would all be given to you. So the distance is 120 meters is equal to the initial velocity from here now, right? So it's almost like this is where I'm starting now, and I want to go from here to here. You can split it into like parts A, B, and C. So from B to C, I'm starting here, initial velocity of 0 times the time that it takes, which I have no idea, but that'll cancel out anyway, plus half times the acceleration. This time acceleration is going to be positive because now the ball is moving with gravity, which means gravity is helping it and positively accelerating it, not decelerating it. And then t squared. And so then I get 120 is equal to 0 plus half times 10 is 5 t squared. I can divide this by 5 over here. I'll get 24 is equal to t squared. And then I evaluate the square root of 24. And again, this would be estimating. So from that, I might say, well, 4 root 6 is probably the best that I could do. So 2 root 6, like that. And then I would just go, well, root 4 is 2, a little bit more than 2, so it's maybe 2 times 2.4. I'm going to say 4.8 seconds, roughly. So this bit takes 4.8 seconds. This bit over here I could work out. Maybe it worked out to be 1.2 seconds. Now I've got the total flight time is 6 seconds, coincidence with the other one. And that's it. So raised platforms just means that you can't assume symmetry. So you have to split it into 2 halves, and I like to separate it and do A, B, C. So that way then my rising phase is from A to B, and then the other bit is B to C. And you just work with them individually. And remember, your vertical components are going to determine everything. All right, so we go. So then finally, we wanted to look at the effects of gravity. So we saw that gravity was the acceleration. So this one's pretty simple to understand now. Is imagine if we had projectiles instead on the moon, right? Gravity is approximately 1/6 of that on Earth. 1/6 of G on Earth. So we'll do a bit of proportionality, and we'll try to work out and see if we can just kind of reason it through with the theory without an actual question. What impact is this going to have on the path? So let's say again we take the ground, and let's say that we're simultaneously on the Earth and on the moon at the same time. And so we're going to draw the 2 paths of the soccer ball. So Earth is going to be in green. And let's say it does that. All right, and so that will be the Earth path. And then the moon path, we'll do that in blue. And we're going to work out, well, what does it do? Does it do this? Does it do this? Does it stop short? We're going to assume that the ball is launched at the same angle with the same velocities. So we can predict all of that using the formulas. In terms of the time that it takes to reach its maximum position, right? On Earth, which again, let's stick in green. So V was equal to U plus AT, so T was equal to V minus U on A. So for max height, velocity, the final velocity is still going to be 0, vertical, and we're just going to use U. We're not even going to put numbers in, because U should be the same for both on Earth and on the moon. And here A is going to be G of Earth. So we end up with T is equal to negative U on G of Earth. And remember, G of Earth would be negative in this case as well, right? So maybe we'll put a negative in like that. So therefore the time is this ratio of U divided by G, like that. If we do the same thing for the moon, let's just cut right in here, because it's going to be the same calculations. For the moon, it's going to be negative U over negative G of the moon. But we can simplify that, cut out the negatives, and G of the moon is 1/6 of G of E, or of Earth. Like that. And so now we have U divided by a fraction. So if we divide by a fraction, we times and flip, so we can keep the GE under there. Dividing by a 6 is timesing by 6 on 1, and then we end up with 6U on GE. And if we isolate the U on GE, we can see now that we've basically said that the time that it'll take to reach this position will be 6 times as long, right? So it'll take 6 times as long. So we can assume that the entire flight path will also be 6 times as long as well. And so then that could be a multi-choice question in itself, right? The next thing is, will it reach a greater height, right? So if we think about V squared is equal to U squared plus 2AS, the acceleration or the gravity is still getting involved. S is going to equal V squared minus U squared on 2A. And again, we can put in 0 for the maximum height, so 0 velocity at the maximum height. Take away U squared on 2 times, well, I'm in blue, so I might as well go G of moon. And then the other one on Earth would be negative U squared on 2 times G of Earth. We can do the exact same thing again. For the moon, I might just come down here to get a bit of space. So negative U squared on 2, and this would be negative 1/6 of GE again, like that. And so again, what we're seeing is we've got this divide by 1/6. So again, we'll see it's going to times by 6. So 2GE times by 6 on 1. So it's multiplying like that. So it'll actually be able to go higher, right? We can reason with that. It'll go 6 times higher. Why? Because on Earth, the acceleration downwards, the deceleration effect is much, much greater, which means it's under greater resistance in its upward movement. So it's under less resistance, which will mean that it'll be able to go less impeded to be able to reach a higher height. Remember, we're ignoring any of the horizontal components to it. So then the final thing is, if it had the same horizontal motion to it, then it means that it was in the air 6 times as long. There is no change in horizontal vectors between the moon and Earth because gravity is vertical. So therefore you've got the same horizontal velocity, which is remaining constant throughout the flight. But the time in the air is 6 times greater on the moon. So therefore the ball should travel 6 times as far as well. And so if we redraw this out, I'll do it down here. Comparing these two, you wouldn't ever need to draw this, but on the Earth, the ball would do, well, I'll try to do it roughly to scale. Like that. And let's say that is 1 meter, just to keep things simple. Then, and it reaches a height of 1 meter. And it takes 6 seconds. Ignore the maths because that probably won't match. That means on the moon, it'll do this under those exact same conditions. And so what this will be is 6 meters. It'll be able to reach a height of 6 meters. And it'll take 6 times as long. So that will mean that this one here, maybe this took 1 second. So this will take 6 seconds to do its thing, like that. So all in all, we've proven what does gravity do? It has a direct impact on flight time, maximum height achieved, and also the horizontal distance traveled, assuming that the launch speed and the launch angle are identical between the two. So realistically, it's a multi-choice exam, right? So now that you know that, as long as you know the ratio of the gravitational fields, then you can immediately know what factor of scale applies to the other thing. So if you're talking about something where it's a quarter of gravity on Earth, then that means it's going to be 4 times greater in all of those 3 different variables. If it's a tenth, then it's going to be 10 times greater. So there's an inverse relationship. And we can actually see the inverse relationship in the formulas because we can see here distance and acceleration, which is gravity, have an inverse relationship in the formula. Time also had an inverse relationship. We can see that over here, time and gravity. There we go. And then we had, distance is equal to speed times time for the horizontal. And the idea is that since gravity had an inverse relationship with time, decreasing gravity increased time, and distance and time are directly proportional. So decreasing gravity increases time, which increases distance traveled horizontally as well. There we go. Cool. All right, so that's everything with projectiles. Okay, so we'll move a little bit quicker on circular motion now. This one, again, more so on the principles of it. I might just go over to the side here. So with circular motion, we just want to understand a couple of different things. So first is that the acceleration of something moving in a circular path is given as v squared on r. Again, all these formulas are given, but we'll just run through them very quickly. Net force is mass times acceleration from Newton's second law. So therefore, in a particle with a mass that is moving in a circular motion, it would be m times v squared on r, or mv squared on r. So if we had, for example, something going around in a circle like this in the flat plane or in the horizontal plane, then the idea is that the radius of its path, given here, looks like an oval, but we're taking like an oblique angle to it. Say a car driving around in a circle. If the car's mass is 1,000 kilos and it's moving with a velocity of 3 meters per second, then it means that its acceleration its circular acceleration is 3 squared divided by, and a radius, let's say a radius of 30 over 30, like that, right? So that would be 9 on 30, which we could simplify to be 3 on 10, or 0.3 meters per square second. If we wanted to know what was the net force applied, then that would be 1,000 mass times its acceleration, which is 0.3, 300 newtons of force. And the key thing is that the force actually, the net force directs itself towards the center of the circle. But what you'll find is that is centripetal force, but centrifugal force is the response to that, which actually pulls outwards, which explains why if you're in a car and you're going around a roundabout, you actually feel your weight pull out to the outside of the turn, not the inside. So we can use that for anything that's working in a circular path. It could also be like a ball on a string spinning around and that kind of thing. So if we had like a totem pole like this, and then the ball spinning around in a circle like that, and we had this length here, we can work out things like the tension on the string, assuming that we know the angle that it makes with the horizontal. So say that was 30 degrees, then we could say that the, let's say the string length is like 10 meters. That's way too big, what am I doing? Let's say it's 1 meter. Then we can use a bit of trigonometry and we can work out the effective radius here. So this would be the radius. So then that would be cosine of 30 degrees is equal to r on 1. So r is equal to 1 times cosine 30, like that. And they'd probably give you the value of cosine 30 in the question. I know from my VCE stuff that we do a lot of exact answers. So root 3 on 2, which should be around about 1.7, so 0.85 or so, we'll say. So we get 0.85, and then we can work out, let's say the ball on the end has a mass of 50 grams. We want to put that into kilos, so 0.05 kilos, and let's say that it's spinning with a velocity of 10 meters per second. We know now that the net force is going to be 0.05 times velocity squared, so 10 squared over 0.85. And let's just do estimates here. So we'll try to be as exact as possible. That's 100 over 0.85. We can then do times that by 100, give me 5 over 0.85. 5 over 1 would give me 5. So 5 over a little bit less than 1 would give me a little bit more than 5. So I'm just going to say around about 6-ish newtons, like that. But the key is that would be 6 newtons directed towards the center, right? So then to work out what force is pulling on the string, I might just go over this way and redraw it and do forces over here. If I've got 6 newtons here and a right angle triangle, I can work out the hypotenuse. So there again, I can do cosine of 30 should equal 6 over the force of tension in the string. So therefore the force of tension is going to be 6 over cosine of 30. And the question says that cosine of 30 is around about 0.85. And so again, 6 divided by 0.85 might put me up to around about 7-ish. I'll say 7.2 maybe. It's multi-choice, so wouldn't really matter. And there we've got tension in the wire. Then finally, I'll go over this side. So now we just want to look at torque, work, and then a bit on potential energies. So torque, they would probably give you the formula for this one as well, but it's probably good to know it. So torque is a rotational amount of work that's applied, or not really work, it's a rotational force. So you apply something at some distance from a pivot point. So say that we have here a lever, this is its pivot point, and we can rotate it in a circle, right? We can spin it around and that kind of thing. What that means is that if I apply a force at the end here, and let's say that this distance is some radius r like that, and I apply some force F, then my torque, which is usually given tau as the symbol, but you wouldn't really need to worry too much about that. It's force times perpendicular radius. The key thing is the radius has to be perpendicular. If the force or the radius is at an angle, then you have to work out the perpendicular component using trigonometry. I don't think that's very likely in GAMSAT though, so I'm probably going to leave that one out unless people really want to see that. So that's really the simplicity of it. So you could think about like pushing on a door, for example. You can apply torque by pressing on the end of the door. If you tried to, for example, I'll try to draw a door here. like that. This can be the doorway behind it. So if you press at this point, you'll find that it's relatively easy to push. The reason for that is because it's pivoting around this distance here. So you're increasing that distance or the radius of torque. Whereas if you try to press closer to the hinges, you'll find you have to press with a lot more force to apply the same torque. And the reason for that is because force, if we solve here, if we solve for force is equal to torque divided by radius. So if you decrease the radius and you want to keep the torque constant, that would mean that the force required has to go up in response to it, like that, and vice versa. And you'll find you could even test it. You get to the edge of a door and you press further and further towards the handle, and you'll find that it gets easier, requires less force to apply the same amount of torque. So how does that help us, right? So if we were looking at like, trying to think of a good example, well, let's say really, really specific, very, very medical, but let's say someone was trying to like use surgical tools to open up someone's rib cage or something. So they'd cut the sternum, or I don't actually know how they do it specifically. That's why I'm trying to get into medical school. But trying to open up someone's rib cage and then using what, forceps, I guess. I don't know the jargon for it actually, but a way of levering the rib cage open, right? So some kind of like tong system like this, where you press and then these ends push out and then open up the rib cage like that. If you had some really, really, really tall ones like this, they would be far, far easier to use overall, because your radius to the hinge point, well, that's gone a little bit wonky, perpendicular radius, which would be that distance there, is much, much greater, which would mean you would be able to apply greater torque with less force overall. And so it would be less straining or less effort to do so. Same concept as like if you've got like a spanner or something. I'll try to draw that out like this, and use the old trick of you put an Allen key through the handle and you can extend the effective radius and then press down, and you can actually get greater torque through it. Or I should say the other way around, if you're using an Allen key like this, you can put the end of a spanner over it like that, and then you can effectively increase, you can hook it over and then effectively increase the perpendicular radius. And then work, very, very closely related to it. So work is just energy dissipated because of applying a force over some distance. So it really just relies on a formula: work equals force times displacement, force times S or force times X, whatever you want to think of it as. So if, for example, you're pushing a box, nice simple example, like this, with a force of 100 newtons, and you push it along a distance of 10 meters, then it means that the work done is 100 times 10, and therefore 1,000. And it is a measure of energy, so therefore that would be measured in standard units, joules, but you could convert that to kilojoules as well. So anything where there's some movement, then work may have been done. If there's force and distance, you've got work. And then finally, potential energy. These ones, we just want to be familiar with the three of them. Again, they'll most likely give you the formulas. We want to understand what they relate to. So I might just zoom in here. So potential energies are just any energy that has the potential to change its form, which is kind of any energy really. So we've got gravitational, which is to do with height. So the higher above the ground you are, the greater your potential energy. It's also connected to the value of gravity, and it's measured, often given UG, it's measured as mass times the value of gravitational field times the vertical height above the surface. So if someone is jumping in the air or something, they have gravitational energy while they're in the air, but it goes back down to zero when they're back on the ground. Kinetic is moving energy. So this one's calculated as half times mass times the square of velocity. So the faster you move, the more kinetic energy you have, but also it's directly related to mass. So heavier things have more of that as well. And then elastic potential energy is to do with springs and elastic materials. And these are half times K times X squared. So K is a constant, spring constant for that specific spring. They will give you that in the formula, or in the stem. And X is the amount of compression, or the change in its length really, overall, right? And that's measured in meters. and you square that as well. So it's very, very similar to the kinetic. And the conservation of energy just explains that energy cannot be created or destroyed. That is the 0th law of thermodynamics. So therefore, in a system, assuming that there are no energy losses to the environment that we can't measure, then all of these energy forms should just be converting between themselves, but there shouldn't be an overall increase or decrease. So if we go back, let's just go full circle and go to the projectile. At this point here, I like to do little lists, so I go UG, EK, and ES. So ES is going to be out the whole time. There's going to be 0 of that because there's no elastic component to this. Its kinetic energy is 0 because it has no motion yet. And then its gravitational is also 0 because it has no height above the ground. As soon as it gets launched though, even before it leaves the ground, it's being given an immediate velocity, right? And so therefore that would be all of the energy would be kinetic, and therefore that's the maximum amount of kinetic energy that is possible. Let's do numbers though. Let's say that that is 10 joules to keep the numbers simple. When it's in this position here, it is now moving. So it's definitely moving, so it's got some kinetic energy, but it's also got some height now as well, right? We'll call that H1. So it's gained some gravitational energy, and let's say that's 5, right? 5 joules. Where does that come from? It's been converted from kinetic. So this will no longer be 10, this will now be 5 joules. You can see it still adds up to 10, and there's obviously no elastic at this point like that. So that'll remain 0 throughout. When we get to the top here, we said before that its kinetic energy is 0. So that means that all of the kinetic energy has now been converted to gravitational. So now UG has hit its maximum at 10 joules, and EK is going to be 0, and ES again is going to be 0. And then when it starts falling, that gravitational starts converting back into kinetic as it starts gaining velocity again. So we'll start to see the UG go down. And you can also explain it because here it was going up because its height was going up. Now its height is decreasing. So UG starts decreasing, back down to say 5 joules, and then kinetic would gain it or pick up the slack, and then ES would be 0, and then finally it hits the ground, and again its UG is going to be back down to 0, and its EK would be all 10, and then ES would be 0. And so throughout, the entire total energy remained constant, therefore energy was conserved. Hopefully that's helped with just understanding some of the kind of key principles of these topics. Like I said, there's lots of formulas in there. They're going to give you all the formulas, so don't fuss about that. It's better to just have a working understanding of what the words mean, the distinctions between forces, energies, velocities, that kind of thing, and also being able to use vector components to be able to qualitatively analyze a particular scenario. Cool. Leave me questions if you've got any. There may be some because we're starting to get into heavier and heavier stuff. Next up in the physics crash course, I think I'll probably go over some of the basics of radiation. That might be a little bit of a shorter one because there's a lot less content that's actually examinable in GAMSAT for that. And then we'll also have another chemistry one coming up too. I might have to go through acids and bases first, but then we'll try to get into organic pretty quickly because I know that's the thing that people are most concerned with. Otherwise, I will